Welding processes has been initially used as the repair or maintenance tool. Then later, it became one of the most important manufacturing methods in various uh, manufacturing industry, like construction, bridges, buildings, storage tanks, pressure vessel, all of them, they are using welding processes. Shipbuilding, even aerospace, aircraft, railroad. You see, automotive industry is using spot welder. All these, robots, they have a spot welder gun. These blue parts are a spot welder gun that are used for connecting, for joining sheet metals together to assemble, the automotive body. Every car approximately contains at least 5,000 spot weld. So you see all this, or spot weld. Later in this lecture, I just explain how the spot weld is performed and what is, the fundamental of it. What is welding? Welding is a process of metallurgically bonding two pieces of material with application of heat or pressure, or both of them together, heat and pressure. So the process can be done with a filler material or without a filler material. And there are many different welding processes. The one category is fusion welding process. Fusion is one family, and it has resistant welding, brazing, soldering. Solid state is not, fusion welding. It's a different category. It has its own category. So we have fusion welding and solid state welding, different category. And in the fusion welding, we have a coalescence that is going to be accomplished by melting two parts that are going to be joined. In some cases, we use filler material. In some cases, we don't use a filler. And fusion welding has, arc welding, different arc welding processes. They have high beam, high energy beam welding processes like a laser beam, electron beam. So these processes, they melt the base metal. And shielded metal arc welding, gas tungsten welding. So GTA is a abbreviation of this gas tungsten welding. Sometimes they call it, TIG welding process. TIG means tungsten inert gas. This one, gas metal arc welding, also it's called MIG welding. And we have flux cord arc, which is similar to shielded metal arc. And in the market, the shielded metal arc is also called a stick welding process. Plasma arc, similar. It is similar to TIG welding process. And the last one is submerged arc welding. In the solid state welding, we have heat, we have we have pressure, and the heat and pressure are used for the coalescence, but there is no melting of the base metal. So also filler is not used. You don't have filler material. Some of these processes are forge welding, diffusion welding, and friction welding process. This is a chart that shows a various group of welding processes. This is prepared by American Welding Society. It's a non-profit organization, and you see we have arc welding family up there, and it contains this this many welding processes. And then we have resistant welding and arc welding. Both of them, in both cases, materials will be melted. Okay, so it is fusion welding. Then we have solid state welding, where the base metal are not melted. Oxy-fuel welding, base metal are melted, so it is a fusion welding process. We have other welding. In some cases, brazing and soldering. In those two cases, the base metals are not melted, but the filler material that are used for joining two base metals, the filler will be melted. In this category, which is high energy beam welding, also the material, the base metal will be melted, and it is called fusion welding. So let's look at the first category, fusion welding processes. In the fusion welding, we may have filler metal that can be used to facilitate the process and provide good strength. In some cases, we don't use filler material. If we don't use filler material, then the process is called autogenous weld. Okay, so we have, for example, two plates. And here we want to weld it, so we don't need any filler material. So because the two surfaces are close to each other, so they can be joined together if we provide enough heat to melt these two base metals, right? And this the configuration is called butt weld. So depending on how you put the metals into for joining process for welding, they have different name. For example, this configuration is called butt weld. We have other configuration. Let's say this is one plate on the bottom, and then we have a plate on top of it. We want to join this area, so this part is perpendicular to the plate A. So plate B is perpendicular to plate A, and this type is called T type. In the fusion welding, in this lecture we're gonna look at three group of fusion welding processes. One is the arc welding, and in the arc welding, the melting of the base metal can be done with the electric arc, right? And then the resistant welding, melting is going to be accomplished by Joule heating law. So we pass electric current through a plate. Because of the resistance of the plate, the material is going to be heated. So the equation is I squared R for let's say heat. If resistance is high and you pass a high amount of current, so that will give you enough heat to melt the base metal. So this equation is called Joule heating law. The next category is oxy-fuel welding, or OFW. The melting is going to be done by oxy-fuel gas. So the gas, we have various gas. It can be acetylene, hydrogen, or other types. So this combustion will provide enough energy to melt the base metal. In the arc welding process, we create a molten metal or a pool of molten metal near the electrode tip. So this area. How? So as you see, if we have the welding machine, it has AC or DC power, and the electron are going to come here through this electrode, and then this electron will travel from the electrode to the workpiece. So the workpiece has to be connected to the machine as well. So there is a clamp, as you see here. And the electron will travel between this gap. The thing is, we have air gap between the electrode and the workpiece. So the air is not a conductive, it's an insulator. So it will block the electron movement. There are some tricks to make the air conductive. It's called plasma. So we convert the air into the plasma. So the last atom of the last electron of the atoms, if the electron are traveling around the atoms, around the neutron or nucleus, initially we provided a lot of energy, to take one of these electron from the atom, and when you take that electron out, so the air has electron. So as once you have electron in the air, so free electron, so the air becomes plasma. Okay, plasma is the fourth state of the matter. We have three states of the matter. One is solid. Ice, for example, is one of them, solid. The next one is liquid. Next one is gas, right? The fourth state is plasma. Plasma is conductive. So we create, a plasma canal between electrode and the workpiece. When you have that plasma, the electron will be able to travel and will be able to travel from the electrode to the workpiece. Once they travel, first of all, we have one equation, IR2. So if you have a lot of electric current, so the energy, you have a lot of energy, right? The next thing is that if the electron are traveling from the electrode to the workpiece, we have the bombard of electron on the surface, the workpiece surface. So that bombard is another source of energy. So that's why we can create, weld by heating, by passing, the electron through the electrode. So that passing creates heat, can melt the base metal as well as the electrode. Or as you see here, we have a filler material, so the filler can be melted as well, and then joint can be created. Here we have three steps of the process. The two parts that are going to be joined together are brought at this interface. Again, this is butt weld, and then we provide energy if we need filler material, for example, to fill that gap. You have some gap, so if you want to fill it, then filler metal is going to be used. And this type, when you use filler metal, it is called non-autogenous welding. Then finally, at the cross section, you see we have this weld. This slide shows you a cross section of fusion welding drum. So this one is base metal. Base metal means that the metal was not affected, so that up to here. So the microstructure, property of that part was not melted. Then we have fusion zone, right? This area is fusion zone. It means that area was melted. A little outside of that fusion zone, we have a area that is called heat affected zone. This heat affected zone is not melted, but it experienced high temperature below melting point, so that was high enough to cause microstructural changes in the solid metal. Okay, and I forgot to mention, this is the weld interface. For example, you can see the microstructure of a weld. At the base metal, we have large grain. These are grain. In the weld zone, we have columnar grain. Okay, and in the heat affected zone, this area, we have HAZ. HAZ experiences a high cooling rate. Because of the high cooling rate, we will get a finer grain. Near the weld, we get coarser grain. And many of welding problems occur in this area, HAZ area. Many failures or crack start at that part. So there are processes to change that microstructure to a desirable microstructure. It is called heat treatment. So what they do after welding, depending on the metal composition, they take the weld sample into the furnace and do a certain procedure, heat it up to certain temperature and hold it at that point. Then microstructure will change. So depending on the material and the application, you can find appropriate microstructure for the application that is intended to be used. The next term in the welding process is flux. Flux prevents oxidation or other contamination in welding process. Sometimes it can dissolve this oxidation during the process. The main task of flux is that it can provide a protection for the filler material or the weld from air contamination. The next the task is to make the arc. If we have arc between the electrode. So if this is the electrode, this is the plate, and we have arc. The flux can make this arc stable. So that is very important. If you don't have a stable arc, it will affect the weld. The shape of the weld, other parameter in the welding process. Also, it can reduces spatters. The molten metal fly. So if you have a flux, you can prevent those spattering, right? That's another task of the flux. The flux can be used different form in the stick welding process, or shielded metal arc welding, or they call it a schma welding process. We have electrode. This is plate, and then we have electrode. It's a rod, metal rod, and it is let me change the color. It's covered. The rod is covered with a flux material, and that flux during welding process will be melted along with this electrode, the metal. So, and then it will stay on top of the, let's say this is a weld, this area is welded, right? And on top of it we have the slack. The slack is that flux. So this flux will stay on top of the weld, and it can be removed. In welding process, we use direct current or DC, as well as alternating current. The direct current, the electric current is not gonna change. The direction of the electron stay the same, and the magnitude stay the same. But in the AC, the electric current is going to periodically reverse the direction, as well as the magnitude will be continuously change with time. Let's see this diagram. This is time, and this is voltage. In DC, we have this behavior. So the magnitude stay the same, but in AC the magnitude goes up, and then it comes back down. And then from here we have negative, here we have positive. So it periodically changes the magnitude and the direction of the electron. So if we have plate, let's say we have electrode, and this is electrode, this is plate, and this plate is connected to machine, the welding machine, and the terminal is positive and this is negative. So in DC we can pick which one is going to be negative, which part is going to be positive, whether it is electrode or plate. So we can pick the terminal. But in the AC, when you have AC, it does not matter, because the terminal is going to switch every 1/60 second. So the frequency is 60 hertz, right? Every 1/60, the terminal is going to switch between positive and negative. AC, as you know, the household, the power is AC, all of them. So you have, if you have a machine designed for AC, it's going to be less expensive to purchase, because there is no additional equipment to convert the AC input to the DC, right? But if you use DC machine, the DC machine is going to be a little more expensive, because you need to have additional component in that machine to convert AC to DC voltage. And DC, it can be used for most of the metals, and it's good for arc control. The arc, it can be controlled better. The first welding process that we want to explain is a shielded metal arc welding, or SMAW for short. This process uses a consumable electrode, and the electrode has a metal rod, and the metal rod is coated with some chemical material that can provide shielding and flux the weld pool. So here inside this electrode, we have a filler rod, and this surrounding of that electrode, we have flux. The flux is going to be melted, and it generates some gas. So this gas is provided by melting this flux. So that gas is going to protect the weld pool from mixing the air contamination with the this metal, because when the metal is hot, it is ready to be oxidized. So we want to protect it from the air contamination. Then these flux stay on top of the electrode, because they are lighter, and it's that flux becomes slag that we have to remove it from the weld. This process can be used for many of material, like steel, stainless steel. You can use it for cast iron, for some non-ferrous alloys. It is not recommended for aluminums, as well as copper alloy. These are reactive material, so we cannot use it for this material. This is one actual welding process. As you see, the welder is doing the process with a stick, and this process also called stick welding, because we have a filler, it's called welding a stick. And the composition of the filler metal usually should be close to the base metal. The base metal, for example, if this is a base metal. And the coating or the flux, this guy, is cellulose material, which are mixed with carbonate, and these are held together by a silicate binder. One of the disadvantages of the stick welding is that you have to change the stick, because the stick is going to be melted, and you need to take a new stick for the in order to continue the process. So that is one of disadvantage because it reduces the production. It increases the production time. And if you use high current for the process, so the flux may melt prematurely. So that's the next disadvantage of this process. The next process is called flux core arc welding, FCAW for short. This is very similar to previous process, shielded metal arc welding. But the problem that we have in the previous one was replacing the stick electrode. So in this process, it's going to overcome that limitation. There are two versions. One version is called self-shielded, where we have a wire, as you see here. So we don't have electrode rod, and instead we have electrode tubular electrode wire, and inside of that wire, that tube, we have flux. And this electrode is continuous consumable tubing, so it is in coil. So this is one way to overcome the previous problem we had. So we have to replace the wire. Now it's a coil, so it's going to be fed continuously. Okay, so the first category is the self-shielded, where the flux is going to provide gas as well as some other material to protect the weld. There is another one, so let's say self-shielded. The next one is gas shielded, and instead of we are using the flux, but we also have to use gas to provide shielding, protecting the molten metal. So they have two versions, self-shielded and gas shielded. Next is gas tungsten arc welding, or GTAW for short. Then another name of this process is TIG welding, tungsten inert gas welding process. This process is one of the arc welding processes, and it uses a non-consumable electrode. This electrode is non-consumable, so it doesn't melt, and it is used to produce a weld, to produce heat between the workpiece and electrode, because a lot of electric current is going to pass through the electrode and then go through the metal, the base metal. And in this process we have to have shielding gas. The shielding gas protects the hot metal from oxidation and other atmospheric contamination. The gas can be argon or helium. Argon, helium, they are inert gas, so they don't react with the hot metal. Also, let's say argon is one of them. Next one is helium. Also, carbon dioxide is used for the protection of the hot metal. This process can be done without any filler material. It's called autogenous. Also, it can be done with filler material, which is non-autogenous. The reason that tungsten, we call the process non-consumable electrode is that we are using tungsten, and tungsten has a high melting point, 300 degrees Celsius melting point. This process is very good for joining aluminum and stainless steel. Here are the advantages and disadvantages of the process. The TIG welding process can produce very high quality welds. We don't have no spatter in the process, and normally there is not much post welding processes. We don't need to clean the surface of the weld. In the stick welding, we have to clean the surface. We have to remove the slag. The disadvantage is that this is slower than other arc welding processes, because mostly the process is done manually, and if the process requires filler, so that is going to be even slower, because you have to feed the filler material. Next process is gas metal arc welding, or GMA. GMA welding. Also, we use a MET for this process, and here in this process we have electrode that is going to be melted, as well as shielding gas. So shielding gas is going to protect the weld. The electrode is going to come and melt it, so the electrode provides no arc. Also, it is going to be as a filler material. So this process is much easier than TIG and a stick, because you just need to push a trigger over here, as you see, and the wire come here, and the wire is going to be melted. You just need to carry the gun. You don't need to think about bringing the torch close, or adjust your gap continuously, right? So when you set the certain gap between the electrode and between the gun and the workpiece, then you're all set. You can keep that gap. But in stick welding, you have to bring your hand close to the weld puddle, weld pool, because the electrode is melting. But here, the wire is coming from a coil or a spool, so it's going to be continuously fed. So this process has a high production rate. Next process is stud welding. Stud welding is one of arc welding processes, and it can attach a stud to a plate. This process uses a high electric current to generate heat between the stud and the work part. First, the stud is going to be located on the work part perpendicularly, right? Then we have a ceramic ferrule around the stud. Then an arc is going to be formed between the stud and the work metal or workpiece. So the arc will melt the base metal as well as this stud. Then the stud will be plunged into the molten metal. Finally, we remove the ceramic ferrule. So when we have solidification, so when the material is solidified, then there is no chance for air contamination to be to enter this inside the weld metal. The ceramic ferrule is going to be removed from the work plate. Here you see, the stud welding process. This is a gun, and this is a stud, and it's similar to arc welding. Other arc welding process, we have a lot of light coming from the between the stud and the work plate, because we have electric arc. Here we have submerged arc welding process. Similar to other welding processes, arc welding processes, we have electric arc that is going to be formed between the electrode and the workpiece. The molten weld, which is here, are protected from atmospheric contamination because we have a blanket of flux. These are flux, and these are a granular flux. It includes lime, silica, manganese oxide, and calcium fluoride, and other compounds. So the flux comes first, and then the arc is going to be produced this area, and so the flux stay on the top, and because we have a thick layer of the flux, right? And also this flux protects the weld, as well as it can prevent a spatter and a spark, right? As you know, arc has intense UV light, ultraviolet radiation, and also we have a fume. This flux can protect the UV light coming out, so it blocks the UV light as well as the fume. Fume and UV light are part of arc welding processes. So this is one advantage, right? If you can protect the bystander or people around it from the UV light, that is one advantage. Once the metal is cooled, this granular flux is going to be vacuumed, then it can be reused depending on the application. And we have a slag. The slag needs to be removed from the solidified bulk metal. And one of the advantage of this process is that it's good for high deposition rate, because the rate of deposition is high in this process, and it is done automatically. It's good for large diameter pipeline for oil and gas industry. This is one of the good methods because it has a high production rate. Submerged arc welding has many applications. Some of them are listed here. It's good for a structural shape, I-beam. I-beam has this shape. And as I mentioned before, it's good for large beam, large diameter pipes. It's good for heavy machinery. It can be used for steel that has a high amount of carbon. It's not recommended for non-ferrous metals. Here we have oxy-fuel welding process. Oxy-fuel welding uses fuel, and the fuel is going to be mixed with oxygen, and then we have a burning process. Combustion actually happens. This process is used to weld as well as cutting metal. This process uses pure oxygen instead of air, because if you use pure oxygen, it can increase flame temperature. And here we have a schematic of the process. We have mixture of the fuel as well as oxygen. The fuel is going to be mixed at the tip of the torch right here. And one of the gas we use in this process is acetylene. We have various gases for oxy-fuel welding. If we use acetylene, they call it oxyacetylene welding process. If we use filler material, then the process is going to be called welding. If you don't use filler, if you just use the torch for cutting, it's called oxy-fuel cutting process. In the oxy-fuel welding, if we use acetylene, we have two reactions, two combustion processes. So in the first reaction, in the first a chemical reaction, we have acetylene that is going to be reacted by oxygen. It generates carbon monoxide plus hydrogen and heat. So this reaction liberates energy, and also it forms carbon monoxide and free hydrogen. This is a free hydrogen. And the process produces 1/3 of the total energy in the flame, and it is called primary combustion process, and it happened in this area. In the secondary combustion process, oxygen from the surrounding air will unite with the free hydrogen and it forms water vapor, H2O. And again, it liberates more heat. And the carbon monoxide is going to be used to unite with the hydrogen. And again, it generates a new molecule. It's called carbon dioxide. And this reaction again liberates heat. In the blue region of the flame, we have 2/3 of the total energy, and it is called secondary combustion process. There are some safety issues that has to be taken care of when we are working with the acetylene welding process. First is that the acetylene and oxygen are highly flammable, and the oxygen is stored in a tank. Normally the atmosphere, the pressure is the 200 bar, and acetylene is colorless and odorless, and it is very unstable at pressure above 15 psi. Okay, so if the pressure inside the tank goes more than that, let's say 30 psi, without being exposed to electric shock, it will explode. So this is very important to not store the acetylene to more than this pressure, 15 psi. And the storage cylinder for the acetylene is unique. They have a porous filler material. If you look at the cross section of the acetylene cylinder, it's not empty. It has a porous structure, so we can control the pressure inside the tank. And also there is a liquid inside the tank. It's acetone. When you add acetone, it can absorb some of the acetylene. It makes the cylinder stable. So acetone can dissolve 20 times of its own volume of the acetylene. And the screw on the valve for the oxygen and acetylene cylinders, they are designed differently, so we can avoid accidental connection. There are various gases that can be used for oxy-fuel welding. MET is one of them. Hydrogen can be used. Hydrogen these days has less use because there are some safety concerns, because hydrogen burns very fast, and it has one reaction. So there are some safety concerns about hydrogen. Propylene is the next one, propane, and natural gas. Among these gases, hydrogen has a higher temperature, and acetylene has a higher temperature than propane and natural gas as well as propylene. We talked about arc welding process as well as oxy fuel welding, and they have different characteristics. Oxy fuel welding, because it has a larger flame, the heat density is low, so you may spend more energy, but you are melting less material. As you see, this sentence, the maximum temperature we can get with acetylene, oxyacetylene, is 3,500 degrees Celsius. But arc welding produces, more heat with higher density, so the maximum temperature is almost double the maximum temperature in the oxy fuel welding process. So these are some of the differences between arc welding and oxy fuel welding process. Resistant welding process is the next joining process we want to look at. In this process, in this category, we join material by heating the plate through equation called Joule heating law equation. So we pass high electric current through two opposing electrodes. So these two electrodes are going to push the two plate together, so it applies forces, right? And then the electron is going to travel from the upper electrode to the bottom electrode, because when you have high amount of current and as well as the high resistance, a lot of heat is going to be generated between the two plates, and the plate is going to be melted. The reason that we have melting at the center is that resistance at this area is higher than inside the metal, because we have some air gap located between the plates. So if you have air gap, so the resistance is going to be higher, right? And the electrode, the material that we use for the electrodes is copper. So if you use copper, you don't have much resistance. So the resistance here is low, so the heat is going to be low in the electrode. So more energy will be spent within the metal. Here we have a spot welding cycle. In the spot welding cycle, as you see, the part is going to be inserted, two sheet metal, that we want to join, and this graph shows the force as well as the time. Here, the next step, the electrode closes. So what happens? Force between two electrodes is going to be applied. So we have this load. Next step, the electric current is going to be turned on. So here you see the cycle, the electric current is on, and we still keep the load until this point. So we need to keep that load because we have some molten material. If you remove it, then this molten material will escape. And we keep that load until the material cools down or is solidified. When it is solidified, the force is going to be removed. As you see, the force comes down, the electrode is going to be open, then the part is ready. There are some advantages and drawbacks for this process. First, as you see, the process doesn't need any filler material, so the base metal is going to be melted and solidified. The production rate is high, and it is good for automation, and the operator skill in this process is low. You don't need much skill to run the process, and repeatability of the process is high. And the disadvantage is that the machine is expensive. The gun that we use to make the spot weld is expensive, especially if you want to run it on a robot. And the next problem with that, it is mostly limited to lap joints. So this configuration is called lap. Resistance seam welding is one of the resistance welding processes. In this process, we have a rotating wheel electrode. This is an electrode, but it is rotating, and it is made of copper. The main reason, as I said before, so it doesn't spend energy at the electrode. And this process can make a spot weld continuously between the two sheet metal. So it's good for sealing purposes. So that's why they use it for the gasoline tank, automobile, muffler, and other, metal container. If we look at the cross section of the spot weld and seam weld, we see these differences. As you see, spot weld are discrete, right? They are separate from each other, but here we have continuous weld. So that's the main difference between these two processes. Next category is solid state welding. The coalescence or joining the material is going to be achieved by pressure alone or by heat and pressure together. This process, we don't use filler material, and each because we have various type of solid state welding, each one has its own unique way for creating, you know, a bond between the faying surface. The faying surface means, you know, the interface of the two plates. One of the solid state welding process is called friction welding. In the friction welding, coalescence is going to be achieved by frictional heat combined with pressure. As you see here, we have a four step for friction welding. With one part is stationary, is fixed, it doesn't move. The other part is going to be rotated fast, so with high speed that will rotate, and then the part is going to brought together at this point, and because we have pressure and we have rotation, movement and rotation, movement and pressure, heat is going to be generated because of the friction. It's called, you know, friction heat. Then at some point, when the metal at the interface is hot enough, it's not melted, it reaches a certain point. For example, aluminum has a 650 degrees Celsius melting point. This process, you just need to reach around 450 degrees Celsius. So it's in plastic mode. The material is in plastic mode. Then more pressure will be applied at that stage. Then the rotation is going to be stopped while we apply, you know, force. Then the part will solidify, you know, will cool down. Then you have one part. There are some post-processing if, you know, it requires some cleaning. For example, you need some machining process to remove this area to make it, you know, smooth. Good thing about this process, no filler metal is needed, no shielding gas or no flux, and you can have two different material. You can connect, you know, aluminum to steel with this process. Here you see one actual sample, the cross section of a friction welding sample. So when you rotate a part, so the part becomes, you know, plastic. Then it this area is called, you know, flash. So this flashing has to be removed, you know, after the process. Here are the application and limitation of the friction welding. Shaft and tubular parts are good, you know, example for this process. They can be processed easily. If you want to use other parts, it can be done, but the way that you want to run the process is different. They call, for example, you can connect two rectangle shape together, and it is called linear friction welding. This process is can be used for automotive, aircraft, farm equipment, where you have dissimilar connection. The limitation is that one of the part that you want to join has to be um, rotational, and flash that excess of material has to be removed. So this extra operation, it adds cost to the manufacturing, because in the third step, as I mentioned in the previous slide, we have some offsetting, so we are pushing the material toward each other. So the part length, you have to take that into consideration, how much of the metal is going to be pushed into each other, so so it doesn't affect the design. Next solid state welding process is friction stir welding. In this process, we have a rotating tool, as you see this one. The tool is going to be rotated along the joint line. So this line is the joint line between two fork pieces, and the rotating tool generates heat due to friction. So the material is going to be stirred, because we have rotation, so it will stir the metal to form a weld seam like this, as you see here. One of the problems in this process is that we have tool wear. So after a certain 1, 2 process or 3 process, the tool has to be replaced, because the tool tip will worn out, and it has a lot of application in shipbuilding and automotive industry, as well as in aerospace, for connecting, for joining thick aluminum parts together, and the process can be used for joining dissimilar plates. The disadvantages of this process is that we have good mechanical property of the weld joint, because we are not dealing with high temperature, so there is no HAZ. HAZ is a small HAZ, heat affected zone, and we don't have much fume or warping and shielding issues. Shrinkage or distortion is less compared to arc welding process, because we have less amount of heat involved in this process. At the end of the process, we have an exit hole. So if you have this process here, there is a exit hole that is going to be left by the friction stir welding process. There is some methods to address it. You can add another plate, so the process can be continued, right? And then it will stop on this plate that you don't need it, so you can cut it. So far we talked about various welding processes. Now we are going to look at two type of welds. We have numerous joint type or configuration, but the weld type is only 2. One is called fillet, weld type. One is fillet, and other one is groove. Okay, so there is a difference between joint type and weld type. So here, this one is lap welding, right? And this is one joint type. This is one configuration, or butt weld. You join this interface and it is called butt weld. So this is again a joint type, it's not a weld type. So in the next slide I'll explain what fillet is and what groove is. The first one is fillet weld. In the fillet weld, we just feel the edge of the plates that are created by corner lap or T joints. So this is a T joint, right? So we have two plates and they create a corner, so we join them. And this is another one. This is a lap. This is a corner made by T joint, right? And advantage of the fillet weld is that it requires no special joint preparation, no machining, no grinding for previous, before welding process. So if you want to make that angle, you just bring the plate together and then you start welding. And the strength of the weld is a function of its size. So that is, if you want to have a good strength, for example here, as you see, this part is not welded, so it is not full penetration. In that case, you need to do some joint preparation. And the fillet weld can be used in arc welding process as well as oxy-fuel welding process. Next weld is groove weld, and it requires some preparation. For example, some machining to make bevel, and here you need to make a bevel, and it is a groove weld. Because of that preparation, the cost of the groove weld normally is higher than the fillet weld. In the groove weld, we have more penetration. The strength in the groove weld is higher than the fillet. For thicker material, groove is preferred over fillet. In this slide, in the next couple slide, I will talk about the safety tips in the welding process that you have to consider before performing any welding process. First, the electric arc in arc welding process produces different type of light. The first light, first of this three is called UV light. Then we have IR light or infrared light. We have visible light. Okay. The UV light is very is the main problem in the electric arc welding process, because if the eyes are exposed repeatedly to this type of light, it is going to be very painful. So it causes some disability or a painful result. And the intensity of the UV light varies inversely with the square of distance between the source of the light and the eyes. And we have infrared light, which is very similar to the light we see in the beach. If you go to the beach naked, without any shirt, after some time, your skin will burn. So this is the same light we have in the welding process. So if the skin, the neck, we have seen many that do not cover their neck during arc welding process, and the neck has some burning effect. So if it is exposed to arc welding, and so that is one of the safety concern in the arc welding processes. So the neck or the skin has to be covered so it doesn't get burned. In order to protect the eyes from the UV light, the welder must wear special helmet. So the helmet has some dark viewing window that is going to filter out the dangerous radiation. And if it is not, if the welder doesn't use the helmet for a welding helmet, then the eye will have a problem called arc eye. Simply, it is eye damage. In the welding process, it is important to pick a right lens to protect the eyes, the welder eyes, right? So here we have the welding current, and we have various arc welding, and this part is for the oxy-fuel welding. And based on the amount of electric current that you want to use and the type of weld, you can pick the right lens. So each are these numbers indicate the darkness of the lens. So the higher number means the lens is going to be darker. And so you see, for example, for 150 we have to pick number 11. But if we go for oxy-fuel welding process or oxyacetylene cutting, we need to pick number 6 or 7. So if you are using a helmet for oxy-fuel welding or oxyacetylene welding, so that helmet or that glass is not going to be recommended for the arc welding process, because the lens number is smaller, so it does not protect the welder eyes. Some more safety tips about the welding process. This part is about electrical shock. In the welding arc welding machine, all of them are based on 60 and 80 voltage. So the voltage is lower than the household voltage. So they design it to this low voltage to protect the welder from electrical shock. and these are safe. For example, in TIG welding process, uh, the maximum voltage that you may get at the electrode, between electrode and the workpiece, is 30 volt. But you have to pay attention. If the machine has an electrical issue, it has to be addressed. So because otherwise it may bring some electrical shock. And also we have to avoid working in a wet or damp condition. Remember, some of the electron welding processes, like electron beam, it is a high energy welding process. It uses 10,000 volt, so it's very high voltage, and it's very dangerous. When you want to do welding, you make sure that you have the right equipment for the process. You have the right ventilation. So because arc welding produces a lot of fume, and this fume might be very toxic, so it has to be taken out. And you have to have a right table, so it's a metal table, and you have to have a tinted curtain, so you can protect the bystander from the arc. This picture clearly shows that how the exhaust can help can help the welder from the fume. This one doesn't have an exhaust, and this one has an exhaust, as you see. So the fume is taken out, and the welder and the fume doesn't go to the welder face. Here we have a proper dress for welding process: glove, apron, and helmet. Safety glasses even under the helmet should be put on, and also this dress shouldn't have a pocket, so because the molten metal may fly, and if you have a pocket here, so it may stuck there. And these are leather dress. It's recommended for welding process, no plastic. A weld is acceptable when it is free of defects, and the weld is going to be strong enough for the desired application. There are some topics in the weld quality. For example, 3 topics are listed here. We want to take a look at them one by one. First, residual stress, distortion, welding defects, and inspection and testing methods. One of the problems that we see in welding processes is the residual stress and distortion. Residual stress is the amount, type of a stress that is going to be left after the process. So if it is a weld sample, we have high amount of stress this area near the weld interface, and it is in tensile mode. If we look at the cross section, for example, we cut it and we see how the stress look like, and we see it's like a bell shape. This is a stress, and this is distance from the weld line. We have tensile stress near the center line, and that causes distortion. And why it happens? It happens because of the localized heating and localized cooling process in the welding. Because we are heating this area, right? This area further away may experience some increased temperature, but these material point will experience more temperature increase because we have localized heating and melting, and we have residual stress near the interface. If you take the sample, if you take one plate and put it in the furnace and raise the temperature to even 1200 degrees Celsius, and then cool it down uniformly, there won't be any stress on the sample. But localized heating is different, and it causes distortion, stress, and warpage. That is one of the main problem in the welding process. Here we have welding process done, and this shows residual stress left by welding, and here shows we have a stress pattern, and it is we have different stress component. The stress along the weld is called longitudinal stress, and stress along this direction is called transverse stress. As you see, both of them are showing we have positive stress, right? This is positive, this is negative. Near the weld we have positive stress because we have tensile stress. This area, it causes this type of distortion, buckling. So it tries to bring these two ends together, right? Because of the tensile stress. Here we have a list of some methods to reduce the warpage. Welding fixture can be applied to reduce the warpage. We can use heat sink to rapidly remove the heat. We can do some tack welding. Tack welding means you join some, for example, here we want to connect this interface, right? So before we weld, we connect some points together and then start welding from this point to here. So these points are called tack welding. And we select appropriate welding condition, right speed, right amount of filler material, and also we use some preheating. If you apply some preheating, so you increase the temperature of the plate before starting, how you can increase the temperature. You can put it in a furnace, or you can use oxyacetylene, um, oxy-fuel welding, to increase the temperature. So it can cover the whole surface, right? Because of it has a big flame. Or you use a stress relief. Once the part is done, the sample is done, you take it to a furnace and raise the temperature uniformly and cool it down, so stress is going to be gone. Also, you have a proper design of the weldment, so that can be helpful to reduce warpage. Here are some of the welding defects, as you see in this picture. And the welding defect is discontinuity in the weld metal, and that significantly reduces the strength of the joints. Some of these discontinuity are listed, like cracks, cavities, solid inclusion, imperfect shape, incomplete fusion, and other defects. You see here we have a transverse crack. This area shows longitudinal crack. We have toe crack. This area is called toe, and this part is called root. First, look at the cavities defects that are present in the welding process. In the cavity, we have two types, and first one is porosity. It is a small void that happens in the weld metal. The porosity is formed because of the gases that are entrapped during solidification, and can be inclusion of atmospheric gases or sulfur in the weld, or other surface contamination. We may have some shrinkage void, and it can happen during solidification. The next defect is solid inclusion, where we have non-metallic material that are entrapped inside the weld metal. One of them is a slag inclusion. So slag is supposed to stay on top, but in some cases it may entrapped inside the weld metal. So instead of floating, so it is inside, and it stays there during solidification. So that is one problem, that it affects the strength of the weld, because we have discontinuity. Other metallic oxide may entrapped inside the weld metal. Aluminum oxide is one of them, and it degrades the mechanical property of the weld metal. The next defect is called incomplete fusion, where the fusion did not occur through the entire cross-section of the joint. All of them, as you see, we have incomplete fusions. Also, weld profile might be a problem. So we want to have it a shape like this. This is a good profile. It is V groove weld joint, but we may have some shape like this, and it is called undercut, right? So the metal was melted away, so it didn't stay at that corner. So this is called undercut. So we may have some underfill. So it should have enough material to fill that area, but it's not there. So it's called, underfill depression in the weld. The last one is overlap, where the weld is gonna spill beyond the joint, but there is no fusion. So there is no connection between that metal and this base metal, and it is called overlap. In this section, we want to look at three methods of inspecting the weld sample. It can be visual inspection, it can be non-destructive, as well as destructive testing methods. The first one is visual inspection, where some human inspector is gonna look at the weld surface, just examine the surface, and the crack, if they are on the surface, cavity, incomplete fusion, they can be detected. The problem is that we can only detect the problem on the surface, and the human inspector must decide whether we need additional tests or not. Here we have non-destructive evaluation methods, NDE, sometimes we call it NDT, non-destructive testing method. And we have 4 methods. Each method can be explained, should be explained one session, but we don't have that much time, and it is not the scope of this course to go through this process in very detail. Here we have ultrasonic testing, where we use high frequency sound wave to detect crack and inclusion inside the part. The next one is radiographic testing, where X-ray or gamma radiation will be used to provide photograph of the internal flaw. So these two are used for internal flaw. And dye penetrant and fluorescent penetrant are used to detect a small crack and cavity at the surface of the part. And magnetic particle also used for detecting discontinuity near the surface of the part. So these two are for the surface, and this is for deep surface. We can also use destructive testing to determine the strength of the weld. Here we have the mechanical testing as well as metallurgical testing. In the mechanical test, we use the parts for tensile test. We use this weld part for tensile test, for shear test. In the Metallurgical or metallography, we prepare samples, we cut the sample, and we'll take a look at the cross section of the part, and we can find how the microstructure look like. If there is a defect, we can determine the defect inside the part by looking at it under a microscope. In this picture, you see several tests, mechanical tests. The first one is tensile test, that is pulling apart the two ends of the weld sample to determine the strength of the part. So here, the strength of this part, this weld will be determined. In this area, is gonna look at the strength of this fillet. This is the fillet that was prepared by arc welding process. And here we can determine the strength of a spot weld by pulling these two parts from each other. And this one is called peel test, where the strength of the part along this direction will be determined. Here, the shear strength is going to be determined, but here we have a peel test that is going to look at the strength along the normal direction.